Data is everywhere, and it's almost always noisy. Our job? Find the signal hidden inside. Today we learn how to turn a messy scatterplot into a clean polynomial curve using one of the most powerful tools in data science, the least squares method. Nogisborg. Just elegant mathematics, matrices, geometry, and the search for the best possible fit. Ready? Let's dive in. Imagine you're a researcher staring at a scatterplot of experimental data. Points everywhere, noisy, imperfect, real. Your task? Find the hidden pattern, the signal beneath the noise. One of the most natural choices is a polynomial. A degree 0 polynomial is a constant. Degree 1 gives a straight line. Degree 2 a parabola. As the degree increases, so does flexibility. But here's the catch. Choose a degree too low and you underfit, you miss the real pattern. Choose a degree too high and you overfit, you start chasing random noise instead of the true signal. To solve this problem efficiently, we turn to matrices. We pack all our y values into a vector. We build a special matrix called the design matrix. Each row contains the powers of a single x value. And finally, we collect our unknown coefficients into vector C. Now here's the beautiful part. The polynomial evaluated at all data points is simply the matrix product xc. The difference between what our model predicts and the actual data is the residual vector, the error. Our objective is minimizing the squared error. Why squares? Because it penalizes large errors more heavily, it's mathematically smooth, and it has a beautiful geometric meaning. Think of it this way, the vector y lives in an n-dimensional space. The columns of x span a subspace, all possible polynomial predictions. We want to find the point in that subspace that is closest to y. That's an orthogonal projection. And how do we find that projection? We apply calculus, set the derivative of the squared error with respect to each coefficient to 0. That leads us straight to the normal equations. These equations in the matrix formulation are simple and elegant. We can solve explicitly for C and we get the least squares solution. This is the master equation of linear regression. It gives us the best fitting polynomial coefficients, in the sense of minimizing squared error. It works for any polynomial degree. Here's the key insight. The solution depends on the data only through the matrix X transpose X and the vector X transpose Y. That's powerful. It means all the information we need is captured in these averages. And the polynomial degree? That's our choice. A free parameter. Too low underfitting. Too high overfitting. The art of regression is finding the sweet spot in between. In practice, it's often useful to have explicit formulas expressions for the coefficients directly in terms of sample averages. Let's start with the simplest case, degree 0 constant regression. Here the design matrix is just a column of ones. The Gram matrix, X transpose X, becomes simply the number of points, n. Its inverse is 1 over n. The vector X transpose Y is the sum of all y values, which is n times the average of y. Finally, applying the master equation, we get a beautifully simple result. C equals the arithmetic mean of y. That's it. The best constant approximation to your data is just the average. Now let's move to the next step, degree 1 linear regression. Here the design matrix has two columns, one for x and one for the constant term. The Gram matrix, X transpose X, becomes a 2x2 matrix containing sums of x, x squared, and n. We can rewrite it neatly using our sample averages, n times a matrix of averages. The inverse of this Gram matrix has a familiar denominator, n times the variance of x minus the square of the average of x. The vector x transpose y contains the sum of x times y, and the sum of y, again neatly expressed as n times the averages of x, y, and y. Now we apply the master equation, we get our two coefficients, the slope c and the intercept c. These are the classic formulas you've probably seen before, but now derived directly from the matrix framework. Now we take it one step further, degree 2 quadratic regression. Here the design matrix has three columns, x squared, x, and the constant term. The Gram matrix becomes a 3 by 3 matrix containing sums of x up to the fourth power. Again, we express everything in terms of sample averages. The inverse of this 3 by 3 matrix is more complex. We need a determinant, which we call delta. It's built from combinations of the averages, a bit messy but purely mechanical. Once we have the inverse, the vector x transpose y contains the sums of x squared times y, x times y, and y, again expressed as n times the corresponding averages. Multiply the inverse by this vector and we get our three coefficients, C2, C1, and C0. The formulas are longer, but the structure is exactly the same as before. The matrix framework handles all the complexity for us, uniformly, elegantly, and without changing the logic. Now we apply the master equation and we obtain the explicit coefficient formulas for quadratic regression. Yes, the formulas look complex, but here's the key, the method hasn't changed. We still solve the same normal equations. We still use the same matrix framework. Only the design matrix has grown. And that's the real lesson. Linear regression, quadratic regression, even higher degree polynomials, they all follow the exact same logic. Once you understand the matrix approach, you've unlocked a tool that scales to any model you can imagine. So what's the takeaway? Least squares is more than a formula, it's a philosophy. A way of saying, I trust the data but I respect the noise. I want a model that explains the signal, not the errors. The matrix approach gives us a unified language for linear, polynomial, or even multivariate models. Once you understand the normal equations, you understand the backbone of modern data analysis. And that's the beauty of it. From a cloud of points to a clean polynomial, all through the power of linear algebra. So here we are. We started with scattered points, noisy and messy. And we found a way, through matrices, projections, and the logic of least squares, to extract a clear mathematical story. The normal equations gave us the coefficients. The geometry gave us the intuition. And the method gave us a tool that works for polynomials, for lines, for almost any linear model. But here's the real takeaway. Least squares isn't just a formula. It's a mindset. It says, I trust the data but I respect the noise. I want a model that explains, not overcomplicates. Whether you're analyzing experiments, building predictions, or exploring patterns, this is where it starts. So next time you see a scatter plot, remember, there's a curve waiting to be discovered. Thank you for listening. Now, go fit something.